Hello, and thank you for joining us for the 6th Annual Global Summit on Kidney Disease Innovations, Vox Populi. The time is now to prevent and cure kidney diseases. This summit is hosted by the American Association of Kidney Patients in partnership with our allies from the George Washington University School of Medicine and Health Sciences. My name is Edward Hickey, and I have the honor of serving as president of the American Association of Kidney Patients. I'm an attorney from California, and I'm a chronic kidney disease patient and have experience as a care partner due to the history of kidney disease within my family. Early detection and timely innovation are pivotal to managing kidney diseases, which affect 850 million individuals worldwide. The adoption and implementation of early screening recommendations and protocols is a strategic priority for AAKP and the global kidney community. The fact is that early screening and early intervention limits the burden of kidney disease on people, family, taxpayers, and health systems. AAKP has spent years advocating in the United States for a federal government recommendation to screen early for kidney disease. Right now, the U.S. Preventive Services Task Force is still debating whether there is enough evidence to support such a recommendation. As patient advocates, we believe the evidence already exists, and you can find it among the millions of Americans whose lives and livelihood have been disrupted by a late diagnosis of kidney disease. Evidence is also found among the millions of families who have lost a loved one to this devastating disease that could have been prevented or better treated. We believe the failure to adopt a national screening recommendation is a negative government determinant of health that must and will be reversed through advocacy. But outside of government, there's an overwhelmingly positive news. Innovation is driving a new generation of highly sophisticated diagnostics and medical practices that result in earlier disease detection. Today, we will hear about some of these new technologies and share valuable insights on how advancements in early screening techniques and care practices will transform patient care. We will explore the latest research findings, practical applications, and the impact of these approaches on patient care and patient lives. With that, I'm honored to serve as the moderator for our session entitled Utilization of Early Screening and Enhanced Standards to Support Early Identification and Intervention of Kidney Diseases. It is my distinct honor to introduce Dr. Kumar Sharma, a leading figure in the field of nephrology and precision medicine. Dr. Sharma is the Hillis Endowed Distinguished Chair in Medicine, the Director of the Center of Precision Medicine, the Chief of the Division of Nephrology, and the Vice Chair of Research in the Department of Medicine at the University of Texas, San Antonio. Dr. Sharma's career is marked by his profound contributions to the understanding and treatment of kidney diseases. His pioneering work in precision medicine has revolutionized how we approach diagnosis and treatment, emphasizing the importance of personalized care tailored to the unique genetic makeup of each patient. Today, Dr. Sharma will be speaking on his research on a predictive method to identify kidney disease in individuals with type 2 diabetes 5 to 10 years before kidney failure. Dr. Sharma's research was born out of the Kidney Precision Medicine Project, a U.S. National Institutes of Health funded research project, and promises to be both enlightening and impactful. Please join me in welcoming Dr. Kumar Sharma to the program.
Thank you, Ed. And I'd like to thank the AAKP and all of the organizers for the Global Summit and at George Washington University for hosting this program. And it's indeed a pleasure to be giving this presentation at the Global Summit meeting. And I'm really excited to tell you about some new developments in identifying patients early for diabetic kidney and heart failure. Here are my disclosures. Diabetes and kidney disease affects 1 in 3 people, and often they may have silent kidney disease and not notice it until it's very late. When patients end up knowing that they have kidney failure, it's often too advanced to do anything about it. And so the silent phase of kidney disease is occurring too often in many of our patients, and they end up on dialysis which has a high mortality rate. In addition to the healthcare problems that patients face, there is a huge cost to Medicare as well, with kidney care costing over $75 billion annually. And more than the budget of all of NIH, NASA, and DOE is the cost of caring for these patients. And unfortunately, we don't have enough funds to really get into the research as to why these patients develop kidney disease and what we can do about it and how to identify them at an early stage. Fortunately, there's a growing recognition that metabolites are key links in what's now being recognized as the cardiovascular kidney metabolic syndrome. And the American Heart Association has really recognized that the kidney seems to be very closely associated with heart problems as well as with diabetes. And our studies have really provided new insight into what could be the metabolites that are linking diabetes with kidney disease and with heart disease. When we think about kidney disease, we have a picture in our heads as nephrologists, and that is a scarring process that's occurring in the kidney. So in classic diabetic nephropathy, in that patients have a lot of proteinuria, there's a lot of scarring material that occurs in what's called the glomerulus of the kidney. And the scarring also occurs in the tubulointerstitial area, but that's less recognized, and that's thought to be more of a feature of what's called hypertensive nephropathy, which is seen on the right, with less glomerular disease, but more tubulointerstitial and vascular disease. And it's these patients that seem to have a silent progression that we're missing right now with our standard biomarker testing. The current situation is that we have a very good biomarker for identifying patients with kidney disease, whether they have diabetes or without diabetes, and that is the measurement of protein or albumin in the urine. When patients have high levels of protein or albumin in the urine, they're at very high risk of developing kidney failure. This is not applicable to all patients with diabetes. Indeed, over 90% of patients with diabetes don't have much protein in their urine, could have actually normal levels of protein in their urine, but some of them are still at risk of developing kidney failure. So how do we identify these patients? So we know that if there are patients with diabetes that have a lot of protein in their urine, as measured by what's called the albumin-urea test or albumin-creatinine ratio, they will be at high risk of developing kidney failure. In fact, if there's greater than 1 gram per day of albumin in the urine, they essentially have 100% risk of developing kidney failure if they don't die of another cardiovascular event before then. And the risk goes progressively down and reaches about 50% risk if they have between 30 to 299 milligrams per day of albumin in the urine. So every patient with diabetes should know their albumin-creatinine ratio number and get it tested annually to know what the risk is of developing kidney failure. The other population that I want to spend some time with on today are those patients who have less than 30 milligrams per day of albumin in their urine, but there are still a substantial number, 10 to 15%, that are at risk of developing kidney failure. So how do we identify the silent group of patients that still have underlying kidney disease? Unfortunately, this population is growing in the US population and perhaps globally as well. Over the last 20 years, we've actually seen an increase in the number of patients with normo and microalbuminuria that develop progressive kidney disease, be it with an eGFR less than 60 or requiring dialysis. So in many studies, this population of non-proteinuric patients that develop progressive kidney failure can be over 50% of the end-stage renal disease population. How do we address this problem? So we've been taking the angle of metabolomics, which is a global survey of all of the small molecules in the urine that can identify patients who may have progressive disease. And the reason that we pick metabolomics is that these small molecules are essentially a functional outcome of proteins and genes. And since diabetes is largely a metabolic disease, it makes sense that the answers could lie in metabolomics. Now, we know that genes and proteins are critically important, but taking this approach where we start with the metabolites and then work backwards to the proteins and genes may be another approach where we can find something that's very translational and we can measure these molecules very quickly in the blood and the urine. So not only do we measure it in the kidney, but can also be measured in the urine and blood in a non-invasive manner. The metabolites are small molecules. They're produced by the body as a result of metabolic processes. And molecules such as glucose that many people are familiar with is an example of a metabolite. Another metabolite is creatinine itself, or blood urea nitrogen, which is used to measure kidney function. But metabolites have many other roles. They can play a role in normal cellular function. They can be identified as patterns that's different in normal versus disease, and could be used as biomarkers to identify patients who might have diseases that aren't recognized as yet. So 10 years ago or so, we started a study using untargeted urine metabolomics in the largest natural history study of kidney disease in the US, which is the CRIC study. We measured over 6,000 molecules in the urine with untargeted metabolomics, and this was an unbiased study. And we measured it at baseline samples of over 1,000 patients with diabetes and very mild degree of kidney disease. And our question was, do any of these molecules predict kidney failure 5 to 10 years later? And it turned out that from the 6,000, about 15 molecules that's shown here on the left side actually do predict kidney failure 5 to 10 years later. And we further did a targeted analysis so we can actually do a quantitative assay for these molecules. And we found that this data held up very nicely, and these molecules did predict kidney failure. So the question now is, what do these molecules signify, and where do we go to the next step, and which of these molecules may be more important than the others to actually be a cause of kidney failure? So there are quite a few questions that we can ask. Which metabolite should we study further? How does it actually contribute to the disease process? Is it causative or just an innocent bystander of the disease? And what we really need is a method to know which metabolite might actually cause disease. So the approach we wanted to take is to map the metabolites at the tissue level by seeing where the normal patterns of cells are in the kidney tissue versus the abnormal patterns in the same kidney tissue. And if we can map these molecules to the sites of disease, perhaps those are the molecules that are really causing the disease. And the approach we took is by combining multiple technologies, looking at molecules such as small molecules and metabolomics, but also connecting it with proteins and proteomics and genes and transcriptomics, but taking the data from a normal human kidney biopsy as well as in biopsies from patients with kidney disease. And this is our workflow, which is quite complicated and took years to put together, but we can now do this analysis in human kidney biopsies using mass spectrometers and cryotome equipment, as well as search engines to identify the molecules. And this is what the data looks like from a spatial metabolomic analysis on a human kidney biopsy. We could see the actual kidney core and the glomeruli that allow filtering to occur through the kidney And these molecules can be seen to be located right at the site of where the glomeruli are. So you can actually see the molecules that's located in different compartments of the kidney. And by doing what's called a PAS chemical stain, we can start looking at diseased parts of the kidney as well as normal parts of the kidney and separate out where these molecules actually reside. And very interestingly, when we used this technology in a kidney biopsy, we found a region of one person's kidney where there was normal levels of the tubules right next to abnormal level of the tubules. So these are what's called atrophic tubules next to regions of fibrosis, and that's characteristic of progressive kidney failure in humans. In addition, we also saw regions of sclerotic blood vessels, which is usually associated with cardiovascular disease as well as kidney disease. And it was fascinating to us that we found one molecule, which is called adenine, to be located right in the region where there were atrophic tubules, fibrotic regions, and sclerotic blood vessels. So this was really striking to us, and we said, aha, this molecule adenine must be playing an important role. And it turned out that adenine was one of those 15 metabolites that was actually identified by our untargeted approach of over 6,000 molecules that we had previously found to be associated with progressive kidney failure. So given that this data came up with the same molecule from two different technologies, gave us a lot of confidence that this must be important and telling us something important about the biology. To further prove that this was true across many kidneys, we looked at several healthy control kidney biopsies where there was a small amount of adenine present, and many diabetic kidney biopsies where we found a consistent increase in the amount of adenine in the patients with diabetes. It was very interesting again to see the adenine was very intense in the region of the sclerotic artery and atrophic tubules. And in addition, these biopsies of patients with diabetes was performed when they had normal levels of albumin in their urine and a normal GFR, meaning that if a nephrologist or clinician would see that patient in the clinic, they would say there's no evidence of diabetic kidney disease in this patient. If we did a kidney biopsy, there would be high levels of adenine in the kidney. What does that mean in a large patient population? Fortunately, we developed a new test where we can measure adenine in the urine in a very quantitative manner. And we found that those patients with high levels of urine adenine were those patients that had more kidney failure. So this high level of urine adenine identified the high-risk patients that would develop future kidney failure 5 to 10 years later. In addition, we can do something about it because a drug like empagliflozin or an SGLT2 inhibitor can actually lower the urine adenine, and we have new data suggesting that it's also lowering the kidney adenine as well as the urine adenine. And so by lowering the adenine, potentially it's protecting the kidney. And we know that empagliflozin is very good to protect the kidney, but not enough patients are getting it at an early stage. So we now can measure urine adenine and identify these patients at an early stage and potentially also start tailoring the therapy so the urine adenine levels go down and we know that the drug is working. So is adenine actually a cause of kidney disease in humans? And the data suggests that it is. And this is based on genetic mutations in patients. So it's a small, rare type of kidney disease where they have a mutation in a gene called APRT. And this enzyme converts adenine to AMP. When this gene is mutated, adenine builds up and causes the production and buildup of additional toxic molecules in the kidney, and the patients have kidney failure. So we know that this pathway is linked to kidney disease in humans. In addition, adenine is a complicated set of molecules, and it can be produced by multiple pathways. So by now knowing that adenine can be measured in the urine and can represent overall adenine accumulation in the kidney, we now have a non-invasive way of quickly measuring adenine and knowing what the risk is to the patient. And we found also that adenine by itself, when it's given to normal mice, can cause all of the injury markers that we currently have available. So we know that adenine exposure increases kidney injury marker 1 in the kidney, as well as also stimulates the molecule called soluble TNF receptor, again in the kidney, and those molecules are also increased in the blood. So we think these injury markers are occurring because of excess adenine production within the kidney, and then those injury markers are then seen in the blood. But those markers are not causing the disease, they're simply injury markers, and the real driving force could be adenine itself. And why is adenine causing disease? We know that endogenous adenine can be a driver of a pathway called mTOR, which can stimulate fibroblasts and macrophages to make more fibrotic molecules and damage the normal structure and ultimately lead to a scarred kidney. So this is a pathway by which adenine is likely to be working to cause more kidney disease. Now, adenine can also be a great marker not only of kidney failure, but also of all-cause mortality in patients without proteinuria. So although we think many of these patients are protected, some patients do end up having cardiovascular disease and having a cardiac event. And we found that this was true when we measured urine adenine at baseline, in that it predicted those patients that would have all-cause mortality as well as kidney failure. And this was found in the United States population, but also in an Asian population, which included Chinese, Asian Indians, and Malays. So this can be a marker for mortality and kidney failure across multiple ethnicities. The location of adenine, as we found, is mostly around scarred blood vessels and kidney tubules, and now we've proven that it's associated with kidney damage and all-cause mortality in people. This has been validated in over 1,200 patients, both in the US and in Asia, and the data is very consistent across diverse ethnic populations. How do we know that it's really causing the disease? And to prove that definitively, we have to block adenine production. Fortunately, we found a way to do that using a small molecule inhibitor of an enzyme that is responsible for most of the adenine in the kidney. And we found that in a mouse model that we can reduce the kidney adenine quite dramatically using the small molecule inhibitor. And it also lowers urine albuminuria, plasma creatinine, and cystatin C levels, which are used clinically to monitor kidney function in patients. So this study actually demonstrates that adenine itself is causing progression of kidney disease in our mouse model. What about other problems in patients with diabetes apart from kidney disease? And we know that many of our patients unfortunately die of heart disease. Is adenine involved in heart disease? Well, we think the answer is yes. When we look at adenine levels in normal human hearts, there's a very low level of adenine present. However, if the patient has diabetes, some degree of kidney disease, and left ventricular hypertrophy, they have a lot of adenine in their coronary blood vessels. And this is quantified here. So adenine is not only produced in the kidney, but also in the coronary arteries of the heart, especially with diabetes. And not only is urine adenine a good marker of kidney failure and mortality, but it's also a marker of heart failure. So in those patients who have low levels of uranadenine, they're protected against heart failure, but if they have high levels of uranadenine, they're at higher risk of developing heart failure 5 to 10 years later. This recognition of adenine is becoming accepted globally, as many studies have now found that adenine is involved in kidney disease and now heart disease, and many investigators, both in the US and in Asia, are recognizing that endogenous adenine could be a key player in diabetic kidney disease progression. What are the clinical implications of our work thus far? We now have a new test, which is urine adenine, where we can identify patients who are at high risk of kidney failure even when they don't have much protein in their urine. We can also use this test to identify which patients may benefit from an SGLT2 inhibitor, and by repeating the test, monitor whether it's actually effective. We also have new data that's coming out which suggests that patients on a low-fat diet may benefit by lowering their urine adenine levels as they're losing weight. And potentially, this could be very important for those patients who are losing weight to see if it's also improving their risk of kidney failure. Finally, with new therapeutics to block adenine accumulation directly, there could be a huge new set of drugs that could benefit patients with progressive kidney disease if our existing therapies, such as the SGLT2 inhibitors, do not work and patients still have progressive disease. So we've learned a lot in these last few years. We've learned that patients who assume they do not have kidney disease if they lack protein in their urine may actually have a misconception. And there's a need for increased awareness and regular monitoring of these patients, even in the absence of protein in the urine. And it's important for early detection and intervention to avoid this false sense of security. And we now are able to do that by identifying new biomarkers that can identify patients at risk even when they don't have protein in their urine. So the future looks very bright for patients as well as physicians in that we're entering the stage of precision medicine. And now with these new biomarkers that we have available, we can actually start practicing precision medicine and identify patients at an early stage of disease, give them the treatment to match their metabolite biomarker profile, and keep them happy and healthy to lead productive lives and not worry about the need for dialysis. If anyone would like further information, please visit our website, or if you would like information on urine adenine testing or clinical studies, please contact our coordinator with the information shown here on this slide. Thank you, Ed, and I'd also like to thank the AAKP once again for giving us a chance to present at the Global Summit meeting. It was indeed a pleasure.
Thank you, Dr. Sharma, for your excellent presentation. I have a few questions I would like to ask you. Dr. Sharma, to the patients across the globe watching this presentation, are you more confident today than you were 5 years ago about the potential for diagnostics and new therapies to save more lives?
That's a great question. Frankly, I can't be more confident and excited than I am right now with all of the new technologies, the huge interest across many groups, and the understanding that kidney disease is so important. And now we have new ways of identifying patients at early stages of disease and many new treatments. So we're able to now match the treatment with the diagnostic pathway. And so we've never been able to do that before. So I think there's a huge a reason for this great excitement that we all have in the nephrology world and for patients.
To the young medical students watching us today, do you think nephrology is evolving and becoming a more exciting field of medicine to be given the potential to save more lives and make an impact on the future?
That's another great question. There's no question at all that nephrology is right at the leading edge of new science in medicine. And nephrology, with all its new technologies, and ability to deliver a new therapy is going to make a huge impact, not only for our patients who will have progressive kidney failure, but also to protect those patients with cardiovascular disease and many other complications of kidney disease that we don't even recognize, such as amputations and potentially cognitive dysfunction, and many other ravages throughout the body by addressing some of the key problems that we can now identify using these new markers of pathways that we've never recognized before that was causing the disease, not only in the kidney, but also in the vascular system.
And finally, Dr. Sharma, to policy leaders and their staffs, do you think we are reaching a point in kidney medicine where innovation in diagnostics can indeed save more lives and more tax dollars? And if so, where do you think the future federal investments should be made inside federal kidney research?
You know, the federal government has actually provided a lot of money towards kidney disease. Unfortunately, it's for taking care of patients who have end-stage kidney disease and improving their opportunity to take advantage of dialysis. However, although that helps to save lives and keep patients going before they get a kidney transplant, there's very little investment in actually understanding what's causing the disease, to identify those patients who are at the early stages of disease and how those molecules might be actually causing the disease and to find new therapeutics. So this time, more than any other time in the history of nephrology, I could say that using the new platforms that are out there, we can do a tremendous amount to understand kidney disease at a very fundamental level with the new technologies, translate that to biomarkers that can really impact precision medicine and dictate the right therapies for the right patient. So there's no question that more federal dollars should be invested in patients at early stages of kidney disease to avoid the consequences of kidney failure. And by doing that, we could improve the quality of life for countless millions of patients throughout the United States and throughout the world.
Dr. Sharma, we appreciate your commitment to upstream kidney care, and we look forward to supporting your efforts in making this predictive test widely available.